Today, we will first talk about, or suppose that we do have a sufficiently high sampling rate. Okay? Suppose we're indeed in this situation. And then, how do we do the opposite? How do we reconstruct a continuous time signal given the sequence, given its samples? So for this discussion, we will denote the output of a D2C converter as something that has been reconstructed. R stands for reconstruction, 重建. Also, we need to let the system know the sampling rate, of course. And it turns out that this reconstruction will do a mathematical derivation. Okay? So the idea is that we will apply a low-pass filter just to get the middle part of the result, to retrieve that middle part back to the time domain. And then to apply a low-pass filter in the frequency domain turns out to be equivalent to convolution in time domain. Again, we have multiplication in one domain, convolution in the other domain. So we'll do a more detailed mathematical derivation to see what thing is it that we are going to convolve with our samples. Okay? It turns out that the result is interpolation. I will cover that. The result is a kind of interpolation, 叫内插法. It suffices to say that any D2C conversion, right, discrete time to continuous time conversion is always, we are talking about interpolation, right? Because we are given sample value and we need to figure out what is in between. What the signal should be like in between samples. Okay, so essentially what we are doing is nature, is interpolation. Okay, and we will cover this in detail. So that's for today. And later, after introducing this interpolation technique, then we will talk about, this is in the textbook chapter, this is going to be section 4.3. Okay? And then later, we'll just cover briefly, this is 4.4. And this is a D2C conversion. So now, the next topic we have is to combine C2D and D2C. Then we have an entire system. Okay? So the next topic is, let's say we begin with a real-world signal that is continuous in time, and we are going to move it from continuous time domain to discrete time domain or digital domain, if you will. So that's a converter right there. Now the result is basically a sequence of numbers, right? So when we talk about signals in the discrete time domain, basically they are all sequence of numbers. This is just 数列. They are just the signals are sequences of numbers. And now we have a signal that is a sequence of numbers. Then we might want to do some fancy stuff here that is called digital signal processing. Okay. Because now we are in the discrete time domain, or conceptually this is already in the digital domain. After quantization, it will be in digital domain. This is something that a computer, a CPU, a ESP chip can process. Right? So here in between, we are going to just process it somehow in the digital domain. So we perform discrete time signal processing or digital signal processing. And the result is still a sequence of numbers. A sequence of numbers. And then, sometimes you will want to just recreate an analog copy based on this discrete time sequence. So here, let's say what we can do is to perform a conversion back to the continuous time domain. Now, the resulting signal is the output of the entire chain. So that's what it is, this section is about. When we concatenate a C to D converter, and something in between, and it will be followed by a D to C converter, the entire chain. Note that if you just look at the system entirely, if we just look at the system entirely, the input is an analog signal, right? The output is also an analog signal. So we can ask the question, then, for example, if you want the output to be the input, but low pass, only preserving lower frequencies, then what should we do in the DSP domain to make that happen? Okay? So this is the concept of discrete time processing of continuous time signals. So that's the idea, the discrete time processing of continuous time signals. Meaning that the input is continuous time, the output is also continuous time, but in between we actually process the signal in the digital domain. Okay, so that's the idea we were just briefly covered. And it turns out that as far as filter design is concerned, when we are designing a filter, an analog filter, if you are experienced, if you have taken any analog signal processing, analog circuit design courses, you know that to design a circuit, an analog circuit, a purely analog circuit, to achieve a certain frequency response is often difficult. It requires a lot of know-how, right? You put transistors around and feedback and you know what I mean. So it's usually very artistic, should I say? It's a matter of art. Okay, but in it turns out that in the discrete time domain, things are much easier. Much easier. You need to design any a filter of pretty much any kind of frequency response. You can achieve. There are systematic approaches that help you achieve the goal. It's easier. So that's why this way of thinking is valuable. Okay? So we will just cover briefly the idea of. So that's a value. That shows the value of discrete time processing of continuous time signal because it's more systematic and you can pretty much achieve any frequency response you want. Okay? So that's our next topic. So let's talk about the first topic, the D to C conversion. Okay, let me move back this board. So here's the thing, okay? Suppose that originally we have a continuous time signal, and has been sampled. Now, if the goal is to reconstruct the continuous signal from the samples, we have argued that all we need to do is somehow applying a ideal low-pass filter in the frequency domain. Okay, so that ought to give us back the original spectrum after low-pass filter, right? That's the idea. Is everybody with me so far? So the idea is that we have. So let's say we are going to apply a low-pass filter. Apply a low-pass filter, and this low-pass filter has a cutoff frequency. And let's assume that the cutoff frequency is exactly is denoted by omega sub c. C stands for cutoff. So let me just redraw this component, this part here. So this is the spectrum after sampling, and so on, and so on. Where this frequency is the sampling rate, actually we'll call that 2 pi. And this is our highest frequency in the signal. So conceptually, we are going to retrieve this part, we are going to apply a low-pass filter. And let's assume that the cutoff frequency here, the cutoff, C stands for cutoff, 截止频率. Let's suppose that the cutoff frequency is exactly sampling frequency divided by 2. Okay, so this is in the frequency domain. We're going to multiply our spectrum with that spectrum with low pass, an ideal low pass filter. So that's in the frequency domain. But in the time domain, so let's say the result of multiplying our spectrum with a ideal low pass is the spectrum of our reconstruction. Here H is the frequency response. H denotes the frequency response of a low pass filter, of that low pass filter. Okay, so let's be more exact. So here the H response will be a constant in between frequency pi divided by t and minus of that, minus pi divided by t. So in between these two, the cutoff plus and minus cutoff frequency, the response is a constant. And elsewhere, outside the response, the frequency response, the gain is 0. We're going to assume that there is such a filter that we can use, and the frequency response is flat in between minus and plus cutoff frequency. And outside, the gain is 0, an ideal low pass filter. And it turns out that the height here, we are going to select the height to be t, the height here. It's not super important, the constant. Let's assume that you'll find the constant gain in the passband. Let's assume that the gain is t. So we have a multiplication. This is filtering, right? Filtering means that we have a spectrum, and we're multiplying it with the frequency response. But in the time domain, multiplication in the frequency domain is equivalent to convolution in the time domain. We know that the reconstructed signal back to the time domain after applying inverse Fourier transform. Applying inverse Fourier transform, the reconstructed signal would be the convolution of our of this signal with what is denoted as h of t, where h of t is the inverse Fourier transform of this ideal low pass response. Okay. So that's a rather simple relation. So next thing we do is to actually calculate h of t. Given its Fourier transform, we can always apply an inverse Fourier transform to get back this is the impulse response of this filter, of this linear filter. Okay? So that's what we're going to do next. So we know that this is just the definition of inverse Fourier transform. If it is the inverse Fourier transform of an ideal low-pass response, that means to perform an inverse Fourier transform, we need to integrate the frequency response the frequency response needs to be multiplied by e to the j omega t, and then we sum them up over all frequencies from minus infinity to infinity, and there is a 1 over 2 pi, factor of 1 over 2 pi. Right, this is just the definition of inverse Fourier transform. So if we agree on that, then to proceed. And this thing here is an ideal low-pass response, right? So it only has non-zero values in between the color frequency, plus and minus color frequency. Right? So we can replace the integral, the range of integral to this from minus pi over t to plus pi over t. That's the range over which we're going to integrate. And we know that in between this range, the gain there has been set to be a constant t. And it's t. So it's pretty straightforward, e to the j omega t. We integrate over all frequencies in this range. So we just continue. And this integral is not hard to perform, right? Each is something, and we can just find the, we can just simple calculus. It's a matter of simple calculus. So here we are, but note that we are going to integrate over omega, not over t, right? So in the end, this exponent jt needs to be put on, right? So here we have 1 over 2 pi, 1 over 2 pi, and t is right there. And then we have jt, 1 over jt, e to the jt omega, and we need to subtract the plug in omega c equals to pi divided by t, and minus omega c. That's not it. The simple method of calculus. So far so good? Okay, so here we are essentially, we need to calculate e to the jt omega color frequency minus e to the jt. There's a minus sign, color frequency over here. That's this part. And this part, the difference turns out to be what? If you subtract that from this, the result is what? Sine, right? 2j times. Oh, by the way, in this entire course, we are going to use j as a complex number. Okay? That is clear. We're not going to use I. J is the square root of minus 1. Okay? So here, Euler's formula tells us that here this would equal to 2j times sine of color frequency times t. Right here. Okay, so we plug that in here, then just do a bit of bookkeeping. We have t divided by 2 pi, and then jt, 1 over jt, and on top we have 2j times sine color frequency times time. So we're almost there. Okay, so 2 and 2 cancel, j and j cancel, right? So the result, if we just put this t, so the result can be written as sine. This color frequency is pi divided by t, right? The sampling period t times the time t. Now divided by pi divided by sampling period t times time t. And this function has a name, actually. This function, if you divide sine of something divided by that thing, this is called, denoted sometimes as the sinc function, S-I-N-C. This is denoted sometimes called sinc of this thing. So the exact name is not that important, but what is important is the shape. So now let's take a closer look at this function. This function is the impulse response in the ideal low-pass function. Okay? I want you to be familiar with this function. Okay? This is an inverse Fourier transform of an ideal response. Ideal low-pass response in frequency domain. Turns out that it has this form, sine of t divided by t. Basically, this it has the form sine t divided by t, and this thing has a name. It's called sinc. So let's kind of draw a picture of the sinc function. So the sinc function. Let's have a few notes. The first note, the sinc function. Well, this form is not well defined at t equals 0. But if t equals 0, the denominator here, the bottom part here is 0. Right? You cannot divide. We have a problem with division by 0. Okay. So in that case, you need to think about the limit. The limit of sine t divided by t using the L'Hopital rule. Okay. So the first note is that this h of t, strictly speaking, you should say it is equal to sinc function. It is equal to this sine pi over t divided by pi over t if t is when t is not 0, and it approaches 1. Okay, when t is 0. That's like the first note we should know. And secondly, as t approaches infinity, let's observe. When t approaches infinity, actually plus or minus infinity, this is an evenly symmetric function if you develop. When t approaches infinity, this function h of t approaches 0. That's a good thing. Right? So the sinc function looks like. So let's draw the picture. Now this h of t is going to have 0 crossings whenever the argument inside here is a multiple of pi. Right? You have sine pi is 0, sine 2 pi is 0, sine 3 pi is 0. Right? So this sinc function are going to have 0 crossings at integer multiples of t basically. So at one sampling period, 2 sampling period, 3, and so on, this function is going to cross the 0. Whereas, as we say, at t equals 0, the function equals 1. And otherwise, it's going to alternate between plus and minus, and eventually it's going to decay to 0 asymptotically. So this is the kind of the drawing, my attempt to draw the sinc functions. Or the impulse response of this ideal low-pass function. Okay, so then based on this, we're going to kind of draw a picture. Next, we're going to draw a picture of convolving our samples with the sinc function. Right? The next thing we are going to, because we're talking about D to C conversion, right? D to C conversion, and in here we argue that the result, the convolution. Right, the convolution right there. So the reconstructed signal is going to be the result of convolution of this like impulse train with the train impulses with h of t, which is sinc. Okay, so let's not develop further. Let's work on this equation a little bit further. Okay? From this equation we have, we know that the reconstructed signal is going to be the convolution of these two things. For that, we know it's the sinc function. So what is this? This is the last time we already talked about this. Conceptually, this signal is in a continuous time domain, but it is sampled. It's also a sequence of spikes, delta spikes. Okay, and the height of the delta spikes are actually the sample values. So here we have shown that we can rewrite this x s of t. This part here can also be written as a summation over all n, where we have a sequence of delta impulses at t minus n times the most sampling period, and scaled by the height that is our discrete time sample values. So therefore, the reconstructed signal is we just copy this, just substitute this term with this summation, and then work it out right here. We're going to just copy that expression, the summation over all n, and this is our one part of the signal, and we're going to compose this entire sum with h of t. That's what we're going to do. So if we just copy that, next, the reconstructing signal is going to be, so now whenever it's a kind of standard tree, okay? So here we have a summation first with the parentheses, like in between here, right? So often we would just move, because convolution is linear, right? So we can move this inside the summation, to the inside the summation. Is that clear? Because convolution, the idea of convolution is a linear operation. Okay, so we can move ht into the inside of the bracket. Okay? So if we do that, then the reconstructed signal will be still summation over all n, and the sample values times, now the bracket goes here. H of t convolved with delta of t minus n times the sampling period. And further, we know that anything convolved with the delta function that is non-zero at a certain point is basically this function taken value at that time. Right? So now let's just proceed. We still have a summation over here with sample values x of n times now h of t minus nt. Basically, h of t shifted by so much, shifted to the right by so much, and we sum over all n. So this is the expression that we are going to take a closer look at. This final result. The reconstructed signal is going to be what? It's going to be determined by the sample values. You need to know that. So from the sample value, that is our discrete samples. Now, to reconstruct a signal in the continuous time domain, what we're going to do is to sum them up, sum all the samples that convolve. But we are going to sum up copies of the sinc function, scaled by the sample value. And the sinc function are shifted in time by so much, and we sum them up. And this is the expression we are going to use and take a closer look. All right? Are we ready? So we are going to take a closer look at what this really is. Okay, so now let's think about this. So now we have let's say if x is n, let me just draw a kind of random. So let me keep it all of them positive either for discussion. Let's say if x and n are like this. Just for discussion, let me just draw maybe one more sample. And now, there's one more sample. And so on and so forth. Suppose that this is our discrete time samples from the continuous time sequence. And then, according to this equation, what we are going to do when we reconstruct the signal, we are going to shift the sinc function to overlap with the sample. Okay? We're going to shift the sinc function. So for every spike here, we are going to put a sinc function. And we are going to scale the sinc function by so much, by this factor. So for example, for n equals to 0, we are going to place a sinc function. That sort of looks like that. It has zero crossing, it has multiple p. So that's like one copy of the sinc function. That is scaled by this height. Okay, so the top of the sinc function matches the height of our digital sample. So that's one copy of the sinc function. That's actually not shifted because it is nature t. Right? But for the next, due to the presence of our next sample, we're going to also place a copy of the sinc function right there, centered around that sample. So let me just change the color. So here, we are going to put another sinc function, but now the height is a little shorter because this sample is shorter. Okay? So we're going to place another sinc function like right here. And so on and so forth. So the next sample, we are hitting a kind of high, a really tall sample. That's all right. But due to the presence of this spike, the sample here, we are going to place the taller sinc function. And maybe now it looks like that, and so on and so forth. Okay? So this is just one. But this is just a drawing. Okay? And let me just complete my drawing. So for the one final sample we are going to draw, we are going to place a sinc function maybe like this. Oh, there's also a small thing here. All right, so hopefully now you have seen that. Now I'm asking you to imagine summing all the sinc functions, sum them all up. Okay, adding them all up. Then in the end, what we get is the result x reconstructed is the sum of everything, sum of all the colors. Okay, and I sum of everything here. So if we just kind of by inspection, okay, I'm inviting you to look at this summation, and then in the end, I hope you agree with me that in the end, the signal line will look something like that. It will pass through all the top of our samples, whereas so in the end we get a copy like that. And note that so that's the idea. That's the idea of reconstructing a continuous time signal from a discrete time sample. Okay. So this is interpolation. Okay. So before we leave for today, let's do a recap. We'll probably talk about discrete time processing of continuous time signal next week when we meet. But today, we have mentioned that if we want to convert from discrete time back to continuous time, and assume that assuming the sampling rate has been sufficiently high to begin with, then all we need to do is to perform a low-pass filter in the frequency domain. And low-pass filter in the frequency domain corresponds to convolution in time domain. So we need to calculate what exactly we are convolving with. Okay? And that thing is the impulse response of the ideal low-pass filter. And it turns out that the impulse response of the ideal low-pass filter is the Sigg function. Okay? So now when we convolve the discrete time samples with our impulse response, what we have, turns out that what we have is interpolation. So in the end, we begin with these sample values, and then we essentially try to figure out what should come in between. We're given the discrete time values, and now we have a way of figuring out what value should be in between. And then in the end, we use some Sigg interpolation. This interpolation is called, naturally it is referred to as the Sigg interpolation. 用这个 Sigg 这个方式来做 interpolation。So that's the idea of, at least conceptually, we can reconstruct a continuous time signal from these discrete time samples. Okay, and so that's about section all I want to share with you today. See you next week on Tuesday. Thank you on Tuesday. Thank you.